non-constant coefficient differential equations, and we'll start with a simple one, and I'll do some ordinary points, and then I'll do some singular points in a future video. So let's start a simple differential equation. Since it's our first example, my first example, let me start with an easy one: y prime plus y equal to 0. This is example 11 from your PowerPoint, so you guys follow through it if you like. Here x equal to 0 is an ordinary point because none of the coefficients have a denominator that's undefined when x is equal to 0. Now I'm going to guess at a solution here, and it's a power series an x to the n as n goes from 0 to infinity. Now I need to find y prime, so I could plug both y prime and y into the differential equation and try to combine the power series. Now your y prime here will be the summation of n times an x to the power of n minus 1, and I have to up the index by 1 because I lowered the power of x by 1 in the process of differentiation. Now I take these two expressions and I will plug it into the differential equation. So I have the summation of n x to the n minus 1 as n goes from 1 to infinity, plus, and then I'll write y, which is n equal to 0 to infinity, of an x to the n, and that has to equal to 0. So here's my converted differential equation. Now I need to combine these two power series, which means the indices and the power of x must be the same. And if you recall from my introduction to this chapter, when I showed you how to combine power series, I'm sure you recall that you start with making sure that the x has the same power when you plug in the index. So if I plug in 1 in the first power series into n, I'll get x to the power of 1 minus 1, which is 0. And if I plug in the first number here, 0 into the power of x here, so I get x to the power of 0. So both x's are starting from 0, so I don't need to take out any terms from either one of them. So now I just have to play the game of give and take to see how I could make the indices and the power of x is the same. Now this one's pretty simple. It looks like if I come to my first power series, and I'm going to erase the yellow markings. So if I come to my power series, and I look at both my power series here, and I look at the first one, it's n minus 1, the power of x. This one is n. So I could add 1 to this to make this into an n. If I add 1 to this, I have to subtract 1 from the index, which will make it a 0. That will match the second power series, and that works. Oh wow. So I'm going to keep the second one as is, an x to the n, as n goes from 0 to infinity. And then the first one, I'll add 1 to n in the argument, so it'll be n plus 1, an plus 1, and x to the n. And from the index, I subtract 1, so it gets 0 to infinity. So now I have the two power series in which both of them start at 0, and the power of x's match. So I could combine these two power series. In other words, I could add them. So I could write this as the summation of n equals 0 to infinity of, I factor out an x to the n. My coefficients will be n plus 1, an plus 1, plus an from the second one. So that becomes my coefficient, and that's equal to 0. Now the only way this will be the right solution, I'll be able to find the ANs, is for me to realize that the only way this power series could equal 0 is for the coefficient to be 0. So, and there's my equation I need to be able to find my constants. So I can just write n plus 1 times an plus 1 plus an, that must equal to 0. Which then, solving for the higher term, an plus 1 is equal to minus 1 over n plus 1 an. So that becomes my equation I need to use to find my constants so that I could have the solution to my differential equation. So now, how can I solve the constants here? Well, I'm going to let n be 0, 1, 2, 3, 4, 5, 6, and I'm going to see what these constants are going to end up looking like. So therefore, I'm using n equals 0, 1, 2, 3, and so on. As many of them as I could until see a pattern or just the instruction given to you by the professor as to how many terms you should use in the final answer. Now let's start with letting n equal to 0. So if n is equal to 0, then I have a1 is equal to minus 1 over 0 plus 1 a0, which becomes minus a0. So a1 is minus a0. You notice that everything is going to, you'll see that everything will be written in terms of a0. Everything, a0 will be the only variable that will survive and be alive. And that's rightly so, because if you look at it, this is a first order differential equation, which means I will have one solution, which means I need one constant. If that was a second order differential equation, then you know in the solutions you have two constants. So when you're finding these constants for a second order, you'll end up with writing all the other constants in terms of two constants. But here you're writing all the constants in terms of only one constant, and that happens to be, it seems like it's going to be a0. So I continue, I'm going to let n equal 1. So this becomes a2 is equal to minus 1 over 1 plus 1 a1. So this becomes minus 1/2, right? Now what's a1? a1 is minus a0. So this becomes 1/2 a0. And you notice again, it's being written in terms of a0. Now if n is equal to 2, again, substituting into the square above, a3 equals minus 1 over 2 plus 1 a2. So this becomes minus 1 over 3 times a2, but a2 is 1/2 a0. So this becomes minus 1 over 6 a0. Moving on to n is equal to 3. Let's try that out. a4 becomes minus 1 over 3 plus 1 a3. So minus 1 over 4, and a3 is minus 1 over 6 a0. So this becomes 1 over 24 a0. So I think this is enough number of terms for us to begin to see the solution. Now, mind you that you could have solved this differential equation just using the separation of variables, the separable differential equation. I give you this example so you could actually solve this using the methods you learned in the previous modules, and then see how it's solved with the power series form. Because remember, you could solve any differential equation using this method anyhow, because it gives you a generalized expanded version of a closed form function, even if your differential equation has a closed form function, which is what you did in modules 1 and 2. So it'll be interesting for you to solve that using what you learned before, your methods of separation of variables, and then do it this way, and you could see how the answers match. Now, well, they have to, because the answer is unique. So now we have the constants, and let's see if we could write the solution to the differential equation. Now, my solution is the summation of an x to the n, and as n goes from 0 to infinity. Which means my solution, if you write it in an expanded form, you'll write it as a0 x to the 0 plus a1 x to the 1 plus a2 x squared plus a3 x to the x to the third plus a4 x to the fourth, and so on. So that's the solution. Now, what's a0? Well, a0, since you notice everything is being written in terms of a0 in my solutions. That's a0, that's a0, that's a0, that's a0. So it looks like that seems to be the underlying constant that everything is being written in terms of. So a0 will just be a0. X to the power of 0 is just 1 plus a1 is minus a0, so it'll be minus a0 x plus a2 will be 1/2 a0, so it'll be 1/2 a0 x squared. a3 is minus 1/6 a0 x cubed. a4 is plus 1 over 24 a naught x to the fourth and plus so on. So you notice here I could factor out an a naught. If I factor out an a naught here, so just like I could write the solution in terms of the constant. So I'll have 1 minus x plus 1/2 x squared minus 1/6 x cubed plus 1 over 24 x to the fourth minus so on. And this should look familiar to you. This you could write this as, so there's the solution, and sometimes you could look at this pattern and recognize a closed form solution for this, so you could write this as a power series. So you write this as, in this case you could, and it's easy to recognize it. This is just a naught summation as n goes from 0 to infinity. Well, denominator is, this is just n factorial. Your numerator, since the sign alternates, it's minus 1 to the power of n, and it's x to the power of n. And there is my solution written in a more compact form. Now you may not be able to always look at the expanded version of the solutions you produce and write that, but if it's pretty obvious, then you could. My main objective is for you to get to this point. This is just icing on a cake or luxury. Thank you.